Manuel and Denis, the floor is yours. You can share your screen.
Yeah, sure. Then hello from my side as well. And Denis is also in the meeting. I say hello from him as well. And I'm going to present Modbus hardware interface for ROS2 control, or our take on a Modbus hardware interface. Is quite the opposite, I'd say, from the talk before, quite low level, small contribution, but I hope it still provides to be useful for people, since Modbus quite commonly used in robotics for connecting sensors or actuators. Maybe first, who are we or where I'm from? I'm from Stogl Robotics. It's a small company based in Germany and Croatia. We are currently about 6 full-time engineers, and we are specialized in control of robotics hardware or hardware, also development of robotics application and prototypes, mainly in the ROS2 world, and integration of clients application into the ROS2 world. Denis, we can see at the top, he's the founder of the company and also one of the ROS2 control maintainers, and I'm the guy on the bottom. So before I dive into what we did, I want to give a little bit of background to for people to better understand what is actually done and how to use it later. So I first want to introduce ROS2 control a little bit. And for those people who don't know what ROS2 control is, you can kind of imagine it as the kernel for ROS2. So you have your hardware. You can see in the bottom of the picture, for example, industrial robots, mobile platforms, actuators or manipulators, sensors as well. And on the top, you have high-level packages, let's call them like Muth2 or nav2, also your application you're focused on to implement. And ROS2 control sits in the middle, and it provides management of the hardware, abstraction of the hardware, and kind of interfaces to interact with your hardware, and also to interact with controllers. So it's kind of a, let's call it, big toolbox with a lot of quite useful tools. Like I already mentioned, we have abstraction from the hardware. There are also some communication protocols and communication, how to communicate with controllers or hardware. And the most important thing probably is lifecycle and access management for controllers and hardware components as well. Also, it provides interfaces towards ROS2 so that you can control or interact with the controllers or the hardware from the ROS2 world. There are also some generic controllers, like, for example, admittance controller, PID controller, joint trajectory controllers. And it also allows for controller chaining, which is quite useful in the case you have quite complex applications with a lot of controllers. Then you can split them in components and chain the input of one controller to the output of one controller to the input of another. And the architecture can be broken down to roughly 2 main components, which you can see here. The one is the controller manager, the other the resource manager. The controller manager is kind of the interface for the user to interact with the system. It allows for loading controllers, switching between controllers, starting, stopping. Resource manager, on the other hand, is responsible for managing the hardware components. In ROS2 control, there are 3 basic hardware component types. They are actuator, sensor, and system. Actuator is read and write, sensor is read-only hardware, and system is a composite of actuators, joints, sensors, or GPIOs. And how the system usually works is you have your hardware, This then creates so-called command or state interfaces. A command interface is an interface from the hardware which allows for read and write access, and the state interface is read-only access to the hardware. And a controller can then claim so-called loans of the command or state interfaces and access the hardware then through those loans. And the command and state interfaces are usually called handles as well. And a little bit of background for Modbus, for people that are not that familiar with it. So Modbus is a quite old communication protocol, but still widely used for communication with sensors or servo motors. And it's based on a client-server architecture. So I've drawn a small simplified picture, which shows the most important stuff for us. So we have, for example, a motor, and then the motor driver comes, for example, with support for Modbus. So we have then a Modbus server there, and usually we would create a client and send our read or write request, and then get the response from the integrated motor driver, which converts it to commands for the server. And Modbus itself supports TCP/IP, RTU, UDP, and serial. And what's important for us is there are different type of write or read or write access, and so you can read single bits, or also sometimes called coils, and they can be read and write, and then they are called bits, or they can be read only, then they are called input bits or input coils, also sometimes discrete input. And beside those, there are also registers, which can also be read-write or read-only access. And further, there's something called libmodbus, which is an open source library for communication with Modbus devices written in C. And our hardware interface we created relies heavily on this. And libmodbus supports RTU and TCP. I focus on TCP here, and it's available for most common operating systems. And it provides connection handling, so you can communicate with Modbus devices, client or server, does not matter. Provides functions for establishing the connection, and it also provides functionality for reading or writing bits or registers. And one thing to note is that registers in libmodbus are of type unsigned int 16 and bits of unsigned int 8. And if you write or read multiple of registers or bits, then it has always to be a multiple of the size of those types. And our approach, this is for to remember like what I told you so far. So our approach is we implemented a system interface in ROS2 control, which integrates the Modbus protocol inside the ROS2 control framework. So if you and with this approach, you then have the usual lifecycle management, and the read and write requests are exposed as command and state interfaces into the ROS2 control framework, and can then be used like any other command or state interfaces. So the Modbus client, the system interface we created, initiates the connection when the hardware is activated, automatically deactivates the connection, and in every read or write step, then the read request is sent to Modbus, and the values are then set in the state interface and published. So like I already mentioned some parts of this. So what the hardware interfaces provides us is like the ROS2 standard way of like interacting with Modbus devices, and it provides handling of connection for us. It also provides the reading and writing of the hardware, which includes the conversion between unsigned ins and double. And it also provides the creation of those command and state interfaces by simply writing a usual ROS2 control XARC file. I will show this later. And this is split in a Modbus client, which is basically handling the connection to the server, the reading and writing. Then we have a Modbus configuration, which defines for state or command interface, which register should be used, how many bits to read, and also how to convert between double and the unsigned ins we have. And additionally, because the Modbus registers usually define some hardware-specific values. For example, let's say we have the run current, then we have maybe values between 0 and 1533, where 0 is equal to 0 ampere run current, and 1533 is equal to the maximal available run current, maybe 9 ampere in this case. And because we want to have some understandable values in ROS2 control, we also provide the setting of an offset or factor to convert those integer values to SI units, for example, to meter or ampere. And how to use it integrates like with the usual workflow, how you would usually create any hardware interface in ROS2 control. So we define a robot and a macro. For example, my servo motor was to control. And then we have to specify which plugin we want to use. In this case, the created Modbus hardware interface. Then we can pass the IP and the port as parameters. They are then used for establishing the connection. And you can also pass a flag if the connection should be persistent or not. Persistent means in this case that the connection is established once when the hardware is activated, and between consecutive read or writes, the connection is hold, and only when the hardware is deactivated, then the connection is closed. If the connection is set to non-persistent, then in every read or write, the connection is established before the read or write and closed after the read or write. And let's say, for example, we want to now to add a command interface. So we want to have an interface to write some value to our servo motor. I take as example a servo motor again. So we might have register 3, which is the position of the motor. The values are given in motor encoder steps. For example, it's a read-write register and 32 bits. And how we could add this now to our hardware interfaces, we add a joint which encodes what the servo is used for. For example, maybe it's a linear joint to move something up and down. Then we create a command interface. In this case, we call it position because we want to command the position of the servo. Then we have to give it how many bits should be written. We have to say how to convert between the unsigned ins and the double values. For this, we have provided the most common cases to convert between this. Then we have to say if it's register, input register, bits or inputs. In this case, for this servo, they are all registers. And then we apply some factor to convert between meters we use in ROS2 control then to command the servos to the encoder values actually used in the encoder. And if you now want to have some read-only access to the hardware, for example, we want to read the run current of the motor. We could do the same by adding a state interface. Then again, we have to add the register, how to convert this time from unsigned int to double. And we can also apply some factor again to convert the values given by the servo motor to some understandable values for human or the user. And with this would be the whole definition. We would not need to do more. We would just need to define this Xacro file, and then the rest would be automatically handled by the Modbus hardware interface we created. We would then have a position interface, which we could create a controller that uses this, or a run current state interface, which we could subscribe to and get the actual values of the hardware. And if there's some specific handling needed in your hardware, you can, of course, just inherit from this Modbus hardware interface a class myservo, for example, which needs some special specific handling during read or write. And one important thing to note is in the onInit method, or as well as the read or write method, you always have to call the functions of the base class of the Modbus hardware interface. Otherwise, the system interfaces or the command interfaces will not be updated. And also the onInit is important, so that the Xacro is passed and the respective command and state interfaces are created, and we know to which we should connect. And the last thing we would then have to do is just change the plugin name to the hardware interface we created ourselves, and the rest would basically stay the same as in the file I've shown before. And that's it so far from my side. You can find this implementation. It's open source, and you can find it on GitHub. Feel free to contribute, or also if you find issues or anything, then feel free to leave us a comment or something. And I hope it might be useful to some other people as well. And of course, if you have questions, then feel free to ask.
Yes, thank you very much, Manuel, for the overview on the Modbus hardware interface. And yeah, the same way, if you have questions, just unmute.
Yeah, thank you for the presentation. Just a quick question about the Modbus field bus. Did you notice any issues regarding the performance, or did you test it in on a bench test or anything?
So we already used it in a bench test, and when we connected via VPN to some remote location, then the connection sometimes failed because there was timeouts. But when we connected directly, when we were at the location, then it ran for a couple of hours without any problems, and there were no issues regarding the speed or something. But you have to keep in mind that Modbus, I think, is not a fast protocol. So if speed is something you need, I think Modbus is not the way to go, as far as I read in my research on it. I hope this answers the question.
Okay, so if there are no more questions, then I will thank you all for attending, and bye.
Thank you.
Bye. Thank you. Bye.
Bye.